Greetings and welcome to our second gravimetric stoichiometry video. This is gravimetric stoichiometry number 2. We're moving on to the next example in our notes. So example number 14, determine the mass of water vapor when 1.00 grams butane is burned in a lighter. The first step is to make a balanced chemical reaction. So we have butane and it's going to be reacting with oxygen, and we're assuming it is a complete hydrocarbon combustion. So we will have C4H10 as a gas, and it will react with O2 in the air, which will always make CO2 gas and H2O gas as well. So water vapor. When we balance this reaction, it's going to be a little bit of a pain in the butt, but we'll go through that procedure either way. So if we have 4 carbons, we want 4 carbons. If we have 10 hydrogens, we want 5 times 2 is 10 hydrogens. And then we see that we have 4 times 2 is 8 oxygens plus 5 oxygens. 8 plus 5 is 13. Now I can't make 13 out of groups of 2, but what we've talked about before is putting a 13 here and just doubling every number for the other coefficients. So let's just double check that is going to work. 2 times 4 is 8 carbons, 8 carbons. 2 times 10 is 20 hydrogens. 10 times 2 is 20 hydrogens. We have 8 times 2 is 16, plus 10 oxygens, so 26. 13 times 2 is 26 oxygens. Good. So we know that this is a balanced chemical reaction. Our next step is to identify our puzzle pieces, and that's really, really important for us to do and for us to label everything appropriately. So determine the mass of water vapor. We're looking for the mass of water vapor. That is the big unknown thing. So we want to write down that we are looking for the mass of water vapor. We know that 1 gram of butane is going to be burned. So we know that we have 1 gram C4H10. Every time I write down a number with a unit, I'm going to label what chemical that information belongs to. So if we are converting from the mass of one substance to the mass of another, well, the only way we can relate amounts of chemicals is by their moles. So we know we're going to have to turn this into moles, and we're going to somehow have to associate that with moles as well. Well, if I have mass and I want to turn it into moles, I use the molar mass. So the molar mass of butane is 58.14 grams of butane per 1 mole of butane. So that's our molar mass. Our molar mass is 58.14 grams of C4H10 for every 1 mole of C4H10. Now we're going to have to convert from moles of this substance to moles of that substance, and then from moles of this substance to mass of this substance. Well, we're going to have the molar mass of our water as well. The molar mass of water is 18.02 grams of water per 1 mole of water. Perfect. So now I have my mass of my butane. I have the molar mass butane, so I can convert that to moles. I have the molar mass of water, and I want the mass of water, so I can convert from moles to mass. But I don't know how I'm going to be able to convert from moles of this to moles of that. Well, if we want to convert from moles of something to moles of something, we need the molar ratio. The molar ratio is always unknown over given. Our unknown is water, so we have 10 moles of H2O in every 2 moles of C4H10. 10. So what this means is that 2 moles of C4H10 is going to produce 10 moles of H2O, and that's how we're going to relate the two together. So let's actually perform our stoichiometry problem. We always start with what we want. Absolutely all the time. Start with what we want. So what do we want? What are we looking for? We're looking for the mass of water, the mass in grams of water. The only thing that has mass in grams of H2O, the only thing is here, our molar mass of water. So I'll start with that. 18.02 grams of H2O for every 1 mole of H2O. So this is a unit that I want. This is a unit that I want to keep. My grams of H2O. That's the same as what my answer is going to be. So my goal now is to cancel out every other unit. Well, how do I cancel out moles of H2O? What other piece of information, what other puzzle piece has moles of H2O? Well, I see that my molar ratio does. Good, so I'm going to multiply by the molar ratio of H2O for every 2 moles of C4H10. What this is going to do is, now that we have moles of H2O in the bottom of a fraction and moles of H2O in the top of a fraction, they now cancel each other out. Fantastic. Oh no! Now we have moles of butane in the bottom. So we're going to have to try and cancel out moles of butane. Well, the only other thing that has moles of butane is my molar mass, but it's written in the wrong way. So I'm going to have to flip this fraction. I have to put 1 mole of butane on top and 58.14 grams of butane on the bottom. So 1 mole of butane on the top divided by 58.14 grams of butane on the bottom. So have we successfully canceled out moles of C4H10? Well, I have moles of C4H10 here and moles of C4H10 here. Lovely. Now we just have to cancel out grams of butane. Well, I know how many grams of butane we started with. We started with 1 gram of butane. So 1 gram C4H10 over 1. I always want to finish off my fractions. Even if there's nothing on the bottom, just write over 1. So let's see. Grams of C4H10 cancel out with grams of C4H10. And the only thing I'm left with, the only unit we have left, is grams of H2O. That is wonderful. That is perfect. That's exactly what we were looking for. So my mass in grams of H2O is equal to, well, 18.02 times 10 times 1 divided by 1 times 2 times 58.14 is going to give us 1.5497 yada 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 grams of H2O. If I look, how many significant digits do we have in this problem? Well, we have 4 here. These are whole numbers, so they have infinite numbers of significant digits. So we still have 4, 4, and 3. So I'm going to have to round to 3. So I will round to 1.55 grams of H2O. Lovely.